So in this video, we're going to look at characteristic banding properties of NMR, or shift properties of NMR. And basically what this means is that we have talked all of this time about functional groups. And these functional groups have electronegativity values. And those electronegativity values affect the way that NMR signals show up on the spectrum. So here we have the 0 mark, which is due to the TMS. And then we might see a line here and a line there and a line here and a line there and a line there. And all of that is due to different signals that show up in the compound, and those different signals are there because of the electronegativity, maybe atoms, or even the electronegative carbon, if there's no atoms other than that show up on the molecule. So there are characteristic banding properties. Do I want you to remember these? And the answer is no, of course. I don't want you to memorize these. I don't want you to regurgitate these on an assignment or a test or anything else. And that's because there's a reference chart for these that you'll always be able to use. So here is basically an NMR spectra. And what I want you to keep in mind is that this is pretending like this is the y-axis of the spectra. And of course, this on the bottom, if I can draw a straight line, and I can't, is going to be, oh God, what is the world is happening here? So this is the x-axis. And this is the x-axis in terms of part per million. So if I start seeing lines that show up on the NMR, what we're going to see is that maybe one of these various functional groups will be present, and that's what's contributing to the signal that we are seeing in that spectrum. In other words, what that means is that if I see some signals here between 2.5 to 4.5, then these signals are probably due to an oxygen, a nitrogen, or a halogen that's connected to a carbon with protons on it. That's what that basically is representing, okay? So if I see a signal that's between 6.5 to 8, then this signal is probably in terms of some type of aromatic ring, like a benzene, but an aromatic ring that has a hydrogen on it, and that proton is getting picked up in NMR due to that delocalization network ring that we're seeing there. So that normally happens between 6.5 to 8. 9 to 12, if you take a look at this area, if you do see signals in the NMR from here, this is typically due to a carbonyl group, a C double bond O that has a hydrogen directly attached, or a C double bond O that has an OH attached, right? There's no middle carbon there at all, unlike some of the ester example problems that we talked about before in the past. These are hydrogens that are directly connected to electron pullers through the carbonyl or through an oxygen in terms of carboxylic acids. Here in the very beginning of the NMR, 0 to 1.5, this is where we see a lot of our saturated protons show up, meaning that these are simply just hydrogens that are directly connected to a carbon, and there's no other like weird functional groups on that carbon to pull the hydrogen lunch money away. So the electron cloud is very dense in these regions. 1.5 to 2.5, these are where our allylic hydrogens show up. 4.5 to 6.5 is where our Venlic hydrogens show up, and those are hydrogens again on a carbon with a double bond on them, right? So that the reason that these are happening, it's all electronegativity. So the double bond area is strongly negative, and that carbon, because it's strongly negative, will expose that hydrogen more. That hydrogen will have more of a positive charge because of that, and because it will line up with the magnetic field a little stronger, it takes more frequency in order to get it to flip. So again, that's what this is all about. Now, this is just a general, what I would call brief functional group chart. And you'll also see probably something like this in your textbook where it goes into more detail. So notice here, this is just breaking down the halogens into one big subset of 2.5 to 4.5. But on this particular chart, we see halogens here of I and Br and Cl and F. And they are actually going a little deeper in detail as far as the values go. So fluorine is 4 to 4.5. Because it's more electronegative. It exposes that hydrogen a little bit more, and it requires more frequency in order to get it to flip. And then chlorine's less electronegative, so that signal happens a little bit lower. Bromine's less electronegative, so that signal happens even lower. And then iodine's even more electronegative, and that signal happens even lower. So this is a more fine-tuned, more detailed breakdown of basically what this chart is providing you at first glance. So if you don't have this chart in your text, you probably will have something that looks like this in your text, and this does the same thing. So here, the I, the BR, the CL, the F, they're all kind of listed there separately with their own corresponding ppm values that come along with it. But notice you also see things like amine groups and alcohol groups and benzyl groups. You see aldehydes, carboxylic acids, the amides. You see Venlic, hydrogens that are on a carbon with one other group. You see Venlics that are on a carbon with no other groups. You see hydrogens that have just an O group on the other side in terms of an ether. You see hydrogens that have a triple bond here as well that has a signal that's associated with it. You see hydrogens on a benzene ring or an aromatic ring. So the list just goes on, and it's just really a reference for us. So that way, when we start looking at NMRs that look like this, we can say, hey, we've got a signal at like 1.8, 1.9-ish, right? I see a signal that's going to be there. So what would be at 1.8 or 1.9? Well, this chart will come in handy for us. So I know automatically it's not going to be a halogen, right? Because these are way higher than what I saw on that NMR that I just briefly showed up. So 1.8, 1.9s, where would those be? Well, it looks like we would be in this general area here. So keep in mind, not everything is listed, but it does a pretty good job about putting the common things that are showing up in the world of organic on a quick reference chart for you to use, okay? In addition to that, keep a look at the charts and the way that they're organized. So if you like this one a little bit better, you'll see the lower ppm values to the left, and it kind of increases as you go down the chart to a 2.1, and then 2.3 to 5.3, it increases as you go down. And then here we see the halogen breakdown, 2.5 all the way down to 4.5, maybe a 4-ish, depending on what they are. So they're trying to put some order to it, but not everything is going to fit into a nice little pretty box for you. All right. Okay, so let's just kind of jump right into this and look at some example problems that now we can use something like a reference chart to go by in order to determine what really I have and how to determine the difference between the two. So this example problem says, of the spectra in 1315, and there's actually two of them, I've not shown you the second one yet, it says one of them is produced by 1-chloropropane and the other one is 1-iodopropane. All right, so I just want to start with those structures for a minute because I want to show you where the complication is at. So 1-chloropropane and 1-iodopropane. So carbon, carbon, carbon. Prop means 3, and then on the first carbon, I see a chlorine, and then the same thing's going to happen with the other one, except we have an iodine as well. All right, so I'm going to put the rest of the hydrogens on this thing just to make it pretty nice and neat like we've seen up until this point. So this one has a chlorine, so there's one bond. There's our second bond to the other carbon, so I need 2 more hydrogens, and then this one will need 2 hydrogens, and this one will need 3 hydrogens. The same thing's going to happen here. So CH2, CH2, and CH3. That gives all of our carbons 4 bonds in total. All right, so now this example problem is going to tell us, now look at this thing, and you need to figure out which one's which. One of these represents the chloropropane, and one of these represents the iodopropane. So here's one NMR, and then watch closely, there's the other NMR. All right, so let's start comparing these NMRs to each other. Notice I see a major signal here, and then a major signal there, and a major signal here. There's 3 big major signals on the NMR. What these other little things are, I don't really care right now. We've not talked about it, and we will, but just not right now. We don't need that information to answer this question, okay? So here's an NMR with 3 signals, and then there's an NMR with 3 signals. The number of signals is not going to help me here, like it has in the past. We've done some of these examples, but they've all been different, and this one's the same. right? This carbon has proton that's on a chlorine. This is a ding dong. This is a CH2, but there's no chlorine on it. So that's a different signal. Ding dong. And then that's a CH3. No other CH3 groups are here, so that's automatically a ding dong. So we get 3 signals there. Just the same as we would get 3 signals here. 3 major signals in the NMR. And that's what we're seeing in each one of these examples. 3 major signals. I'm seeing a major signal that is here, and then I'm seeing a major signal that is here, and a major signal that is here. Well, this signal is at a 1, and on this other one, it's about the same. Look at that. 1 signal, 2 signal, 3 signal. So the first signal, they're both about 1s. The next signal here, it's a little bit before 2, and then this one is a little bit before 2. So it looks like those are in the same positions, give or take a little bit, right? And then here with the first one, it looks a little bit above a 3. So I'm going to say like a 3.2-ish, a 3.3-ish. And then for this one, it's shifted a little bit further up. This looks like a 3.5 or a 3.6-ish. So it looks like a lot of this is almost identical, right? Especially with the first 2 signals. They look very similar to each other. And it looks like the major difference here is this third signal that's more up or downfield. It's more downfield versus the other signals. All right, so this 3.2-ish versus this 3.5-ish. And we're just supposed to look at this and figure out which one of these is chloro and which one of these is iodo. And the answer is, yeah, you are. You're supposed to. It's going to be easy. Look at this. Here's the chart. And it looks like an iodine, if one of these is iodo, is 2.5 to a 4. And then it looks like chlorine is a 3 to a 4. So it looks like the chloro group happens a little bit more downfield. It has a higher value in terms of ppm than the iodo group is, right? If I look at this chart, it's kind of telling me the same thing, right? I have an iodo group that's 2.5 to 4, and then I have a chlorine that's more of a 3 to 4. So this chlorine will have a higher signal than the iodo group. The chlorine will be higher in ppm than the iodo group. That's what the chart tells me. So this is a 3.2 and this is a 3.5-ish. Go back to iodo group on that, 3.5-ish, right? Iodo could fit in there, 2.5 to 4, right? 3.5 is right in there. Chlorine, 3 to 4. That chlorine could fit in there, right? So it looks like either one of these could go both ways. But if this is a comparison, and that's all that they want me to do, is just compare these 2 NMR spectras to each other, then I'm going to use that as a judgment call. And it looks like in this second NMR that has the higher signal in the 3 to 4 range, well, this maybe, just maybe, might be the chlorine, because chlorine's more electronegative. And that chlorine, because it has a higher electronegativity value, exposes the proton even more to the magnetic field, and that gets harder to flip and provide a signal versus the iodine version that I might have in the other example. All right? So what that means is that for this particular problem, this second spectrum that I'm looking at right now on the screen, that second spectrum is probably the CH2 with the chlorine, CH2, CH3. 3 signals. I see 3 major signals in the NMR. The one that's furthest away from that chlorine will be the most shielded, the most protected from the magnetic field. So it's not going to take a lot to get those to flip. So this signal probably goes to that one. This is the next furthest away. So that is probably this one. And this one is the closest to the electronegative atom, the most exposed, the most positive out of the bunch. the strongest to align with the field because it's the most positive, and it takes more energy to get it to flip. So that one is probably from that signal there. Okay? So that's all that they want us to do with this one, which means that this is the iodo version probably. So a CH2 with the I that's hanging off, and a CH2 and a CH3. Just like before, 3 signals. We already knew there were going to be 3. This is the furthest away, so this will be the easiest to flip. That's happening at a 1 ppm. This is the next furthest away. That will be the next easiest one to flip, and that's happening right before a 2 ppm. And this is the closest to the electronegative atom. That will be the hardest to flip, and that will happen at a little above a 3 ppm. All right, so point of reference, again, it's all about tying all of these together into one nice little package. All right, so this next video is going to concern integration. It is a completely different topic. It's a little bit of math, but because it's a different topic, I'm going to end this video now. So in the next video, we'll pick up with this topic of integration. What does that actually mean in NMR? What do we do with integration? What kind of information are we going to get from integration in NMR? How can we use it to our advantage? How can we use it to help determine the structure of an organic molecule? That is what this next video will be about. So now, again, would be a pretty good break for you to take. Come back with a fresh mind, come back with a fresh sheet of paper, come back with a sharpened pencil or a full pen, because you're probably going to need it, especially when we begin to talking about all of the math that's getting ready to happen. Stay tuned.